Damon Wilson asks, can you teach me molecular mass? So I actually went through this topic of molecular mass already. I did this I did this on Tuesday, actually, the topic of molecular mass and molar mass. However, if you want me to I'll actually go through molar mass. Like if you want, I can do a super quick rundown. I'll literally do it now before I answer this question. So I'll teach you in like 2 minutes here. So if you're talking about molar mass, and Zachary says hi. Hi, Zachary. Molar mass or molecular mass is this topic of basically, if you know, in molar mass is you're given basically how much mass of it, how much the element weighs in terms of mass, so in terms of grams per basically a mole of a substance, right? A mole of a substance, and we know that a mole of a substance is. And we learned about kind of moles in your basically in your junior level chemistry course here. And grams per mole is simply just whatever the molecular mass is. So this is grams per mole is measured. That's kind of the units for molar mass. And basically you have grams per mole. So if you have 1 mole of a substance, 1 mole of a substance, and we know this because of Avogadro's number, right? It equals the Avogadro's number of atoms in that 1 mole of substance. So it's 6.02 times 10 to the power of 23 basically atoms per mole of a substance. So if I have 1 mole of carbon, I'm going to have 6.02 times 10 to the 23 atoms of that of carbon in that 1 mole. So if I say grams per mole, it's basically saying how much it weighs, right? How much that 1 mole substance weighs. So 1 mole of carbon weighs exactly, and we can look at the periodic table here, it exactly weighs 12.011, right? So that's how we determine the atomic mass here. And this is the molar mass, which is the molecular mass. So again, 12.011 would then equal, so if one mole of carbon atoms is equal to 6.02 times 10 to the 23 atoms of carbon, 1 mole of carbon, there will be basically this weighs 12.01 grams of carbon per mole of carbon. So that's kind of this topic of molar mass in like two kind of 2 seconds here. But what you can do is, if you're having trouble with molar mass, what you can do is, again, a formula that you really need to know in chemistry is moles equals mass over molar mass. And that simply just says moles equals mass, which is measured in grams, divided by molar mass, which is measured in grams per mole. So a lot of times what questions are asking, oh, what is the molar mass of a specific question? What you can literally do is just go into the periodic table and add all those masses up to figure out your molar mass of the compound here. So I hope that helps, Damon, in terms of what this question is asking. This is more so grade 11 chemistry topic in terms of stoichiometry and moles and molar mass here. But I hope that helped. Again, I only taught in 2 minutes, so I hope that helped in terms of explaining this topic here. Sweet. So where was I? I was question 3. Then let's work on question 4. So question 4. Let's calculate the pH for each of the following cases in the titration of 50 milliliters of, this is HClO, so this is hypochlorite acid plus potassium hydroxide. The ionization constant for hypochlorite acid can be found. Where is I don't get the Ka here, which is weird, before addition of any potassium hydroxide at 25, after addition of 30, after 50, and after 60 here. No problem, David. Okay, so let's see here. Titration of 50 milliliters. Okay, so I have, let me just write out these constants here. So I have 50 milliliters of, this is 0.200 molars of, this is hypochlorite acid. And then I have with basically 0.20 molars of, this is KOH here. And this here is potassium hydroxide. So I simply have, this is a weak acid, strong base titration here, right? A hypochlorite acid here is a weak acid, and then I have a strong base. So classic titration here, classic weak acid, strong base titration. And then it says I have a ionization constant can be found. I don't know where that is. So I have to actually basically find out where that is. So let me just find that for you. So this is asking me, what is the ionization constant for HClO, because I need to know that. So this is hypochlorous acid, sorry. It's hypochlorous acid. It's 2.81 times 10 to the negative 8 here. This is the Ka, right? Yes, negative 2.81 times 10 to the negative 8. So this is the Ka, which is 2.81 times 10 to the negative 8. And it says, okay, so it's asking us A, which is before addition of any KOH, right? So before we even add base, what is the pH of the solution here? So before we add base, so we only have acid. So let's say we only have 50 milliliters of our acid here. So in order for us to find out we have to first write out our chemical formula, right? So we have HClO aqueous is going to dissolve in water, right? Water is our kind of solution here. It's going to dissolve in water. It's going to be in an equilibrium, and what I'm going to get is I'm going to get H3O plus, which is our acid, plus ClO minus, which is our this here would be our conjugate base here. So again, I have 50 milliliters of 0.200 molarity, which means my concentration of HClO is 0.200 molarity here. And what I can do is I can simply just use an ice table to figure out what the ionization constant, or with the ionization constant to find out what my concentration is. So I'm going to use an ice table. So let me just so I have this is ice. And I basically use this for any equilibrium reaction, right? So initially I have 0.200 molars. The water in this case does not play a part, so I can throw an X in there. Initially I have 0 acid and 0 conjugate base. I'm going to subtract some sort of X here because I don't know how much is going in terms of how much acid I'm producing. I'm going to get some acid and some base, and therefore in the equilibrium I'm going to have 0.20 minus X. This will simply just be positive X and positive X here. So what I can do is now I can write my equilibrium expression, and I can say that it's going to be equal to 2.81 times 10 to the negative 8. 2.81 times 10 to the negative 8 will equal basically my products over my reactants, right? So in this case, it would be the concentration of H3O plus times the concentration of HClO minus over this would be the concentration of hypochlorous acid, right? And again, water doesn't play a part in my concentrations here. Again, I can fill out that this here is 2.81 times 10 to the negative 8 equals, I have X times X, so I have X squared at the top. HClO is 0.200 minus X. I'm going to use the assumption method that this X is going to be super, super small to avoid using the quadratic formula. So I can simply just cross this out. I'm going to multiply both sides by 0.200. So let me just use my calculator here. I have 2.81 times 10 to the negative 8 times 0.200. That's going to give me a value of 5.62 times 10 to the negative 9 equals X squared. I'm going to square root both sides to get X would finally equal 7.50 times 10 to the negative 5, and this would equal the concentration of my hydronium ion. And once I get that, I can simply just use, I'm going to do this in blue, I can simply just solve for the pH using, and am I solving for the pH? Oh, yeah, I'm right, calculate the pH. Negative log of the hydronium ion here. So negative log would equal basically 7.50 times 10 to the negative 5. In this case, negative log would then equal, the pH would then equal times 10 to the negative 5 would give me 4.12. So pH before we even add any base would be 4.12 here. So this here would be my solution for part A. So this is a lot of work to do part A, but basically you do the exact same thing for A, B, C, D, and E. So maybe I'll do one more, I'll maybe just do B, but basically you're repeating the same parts. So let me just check my answer real quick and see what if we verified our solution correctly. So part A is saying that they use exactly an ice table like I did as well. They drew out the ionization or the ionization reaction. That's perfect. And they use an ice table. They gave us the ionization constant is 3.0 times 10 to the negative 8. I wrote 2.81 here. So my answer might be different here, but it should be around, I have 4.12. This is 4.11. This here is basically the same thing. So this is exactly correct they have the ice table here, x, and you have x squared. So you have x squared, and they use approximation method because k is very small. I use the exact same thing when I cross out this minus x here. I'm square rooting both sides for basically 5.6 times 10 to the power of 9, which I get 7.746. 7.50 is probably the same thing here, and then I use the negative log of the concentration of hydronium ions to figure out the pH, which is 4.12. This solution here is correct, so part A is correct here. So I'm going to just do one part. I'm just going to do basically the B for the sake of time, because again, I don't have that much time today, and this question is very, very long. So I'm just going to basically verify the solution here before we start. So let me just do part B for you, and then we will figure this out. Part B states that after adding 25 milliliters of base here, so I'm going to say that now I have 50 milliliters of 0.200 moles of hypochlorous acid, and then I added 25.0 milliliters of 0.200 molars of KOH. So now my titration has begun, right? I've added acid and some base, which is great. So now what I have to do first is I have to find out what the moles of these two things are before I find concentration. I'm going to have a new total volume, right? Because I'm going to add these two volumes together. So let me find the moles of HClO first. So moles of this would be simply concentration times the volume, right? If it's concentration equals N over V, then moles equals concentration times volume, right? So I have this would be equal to concentration, which is 0.200 times 0.05 liters, right? I changed 50 milliliters to liters here. This would get me a solution of 0.2 times 0.05 would give me 0.01. This here would be the moles of HClO. And finally, the moles of potassium hydroxide do the exact same thing. I have 0.200 moles. I'm multiplying it, however, by this is 0.025 liters here. And then, sorry, that does not look like a 0. And then I'm going to get a solution which is 0.200 times 0.025 on my calculator. I get get basically 5 times 10 to the negative 3 here. 5 times 10 to the negative 3 moles of KOH. So these are my moles of KOH here. Basically what I can do to these moles, I can divide it by the total volume, and the total volume in this case is 50 plus 25, right? So 50 plus 25 here is 75.0 milliliters is my total volume. So I have a new concentration of both my acid and my base, right? So I'm going to basically divide both of these guys by 0.075 liters to get my concentration of my acid and my base, right? So this here would be 0.01 divided by 0.075. 0.75, I would get a value of this is 0.0133 molarity of this is HClO, and this would be 0 or 5 times 10 to the negative 3 divided by 0.075. I would get 0.066 molarity here. So again, I have these are my new concentrations for my ice table, basically, that I'm about to do here. And what I'm going to do is I'm going to do the exact same thing, figure out an ice table, and I'm going to figure out again what the concentration of my hydronium ions, so I can figure out my pH. So basically that's kind of the first step to figuring out what that is. Basically I use these concentrations again, I draw my chemical formula, I do my ice table, and I'm going to solve for it. Again, for the sake of time, because I'm only on, this is what, question 4, I'm going to just simply just skip this step because I've already showed you how to do an ice table. So I'm going to just simply just verify the solution here for part B. And because again, this is a very, very long solution here. So again, they have here, this is HCl plus KOH is KClO plus H2O. That's good. And then what we have here is HClO plus hydroxide will give us our ClO minus an H2O, right? So this is our net ion equation. That's good. What they're doing is, again, they're solving for their moles like I did as well, 0.01 and 0.005. And then what they did was they're going to do an ice table to figure out which one's my limiting reagent. Again, my limiting reagent in this case would be, again, not my limiting range, sorry, I'm using my ice table. I have 0.01 as my acid and 0.05 as my base here. This will be the initial concentrations. I lose 0.05, I get 0 for my base here, and I get 0.005 for my acid, which means my X value would be 0.05. And simply what you can do then is you have basically the concentration of your HClO and equals the concentration of your ClO and H2O, right? So again, here at equilibrium, we have an acid and its concentrated base, ClO minus. Therefore, you can have a buffer system. And this is actually more so university level chem than grade 12 chem. Grade 12 chem would have actually probably got you to do the first part like I did, but because this is a buffer solution, because we have our acid and our conjugate base are exactly the same, pH would equal pKa. So the pKa is simply just negative log of our Ka value, which was 2.81, I believe it was 2.81 times 10 to the negative 8. If you do negative log of this number, you would get the pH after this here. This is at pH, this would be at the half equivalence point to figure out what this solution here is. So again, you can use the Henderson-Hasselbalch equation to figure out the buffer system, which is pH equals pKa, so P negative log of Ka of this, plus the concentration of base over acid. In this case, the ratio is 1, therefore pH equals pKa. So therefore, it's 7.52 when it's at half equivalence point. So this is more so a university level question, but when I was picking it, I picked the first part to show you kind of the ice table, which is part of the grade 12 kind of concepts here. I'm going to briefly skim over part C. Again, very similar to part C. You have, again, new moles here. Again, you have 40 milliliters instead of 25. You calculate, do the exact same thing in ice table, and then you do the exact same thing, Henderson-Hasselbalch equation, and you get a pH here, which looks pretty good to me. Yeah, the math checks out here. And then D here is you add 50 milliliters, you do the exact same thing, and you realize that in this case, you have reached equivalence point. Moles of acid equals moles of base. Therefore, you have 0 and 0 in terms of your initial acid base, which means you only have your products here. So in this case, your pH would be let's see, let me see. pH of the solution is dependent on the concentration of the substance. So in this case, it's a pH of this would just be 0.01. So you can find the negative log of that to figure out your pH here. So pH when this is 50 milliliters. What they're doing here is they have, again, 0.01. Again, they're drawing the ice table here, but they realize that they've used up all their base, which means the only thing that's participating in our reaction is our ClO minus and ClO minus right here. So again, ClO minus, you minus some sort of X here, you get this Kb expression. And again, what you have here, or so you get a K expression here. And again, what we're doing here is we are solving for then our Kb expression, because again now we're adding more base than acid here, so we want to use our Kb. Therefore, we solve for our Kb using Kw, which is 1 times 10 to the negative 14, and then you solve for your Kb, which is great. Then you could write out your equation for the dissociation constant. So again, ClO plus OH minus, the hydroxide ion over your ClO minus. That's good. And again, you have your ice table here. You substitute here. You get X equals 1.825, which is equal to a concentration of hydroxide ions. So now you can use PO power of hydroxide equals negative log of the hydroxide ion to get POH, and then you simply subtract 14 minus that to get your pH here. So again, this here is the exact same thing as part E here. So I'm going to say this solution is great. So this is actually a perfect solution here. Perfect solution and answer. However, this solution is actually not that hard. Perfect solution and step-by-step analysis. So remember, we're doing the exact same thing, right? This question is simply just saying, oh, we have to find the moles of it first. Well, after we find the moles, we divide it by the total concentration, which is exactly the same here. After that, and then we're figuring out, okay, which one goes to which. We have our initial concentrations. We're going to subtract it by basically which one gets used up first, and then that will be that we're going to make the conjugate acid and the conjugate base of that. We write out our dissociation constant. We solve for X, which will be our concentration of our hydroxide ion, and then we simply just use pH equals negative log of our hydronium ions, not hydroxide, hydronium ions to figure out pH. And we basically do that 4 times. But however, the moment we switch to adding more base than acid, we have passed our kind of equivalence point. We need to swap our Ka. So we have to actually rearrange algebraically to solve for our Kb, and then we do the exact same thing, but instead of solving for the hydronium ions, we're solving for hydroxide ions. And instead of solving for that, by solving for hydroxide ions, we can solve for our POH, which then we could convert to our pH by using 14 minus POH here. So the solution is correct.